All right, we're talking definite integrals today. And a definite integral is slightly different from an indefinite integral, which is what we've been doing so far. Um, you know what? Let me just scroll down here and I'll explain what it is. Okay, so first you think about the indefinite integral. That's what we've been doing so far. In the indefinite integral, I'm giving you some function, like f prime. I gave you some function, and I said, give me the one above it on the food chain, right? I said, here's some function. Tell me what comes before it in our chain of differentiation, I guess I could call it. If I gave you this one, I'd say what comes before it, right? I find the antiderivative, which is just the function that goes before it. And so say, for example, I gave you 3x squared. Well, and I said, give me the indefinite integral of that. Well, you would tell me that the indefinite integral of 3x squared is x cubed plus c, but it's x cubed, right? So I gave you a function, you gave me out a function, and that function is just that. It's like another curve. I gave you one curve, and you spit out a different curve. But if you remember back to derivatives, this is exactly how it worked too. I gave you a function, you gave me its derivative, gave you another function, you gave me its derivative. But then you could also, with derivatives, you could say, well, when x equals 2, what's the derivative at that point? And we could plug 2, say, into this middle function and get out 12. So we could find an actual number that gave us the slope of the tangent line, couldn't we? Well, integrals are very similar in that sense. So we've got these indefinite ones that we've been learning so far, but we also have these definite ones. And the definite ones basically are talking about curves. And say they talk about this curve, the x cubed curve, and basically what the indefinite integral tells us is the space underneath the curve in between 2 points. So it says at this point, we'll call it A, and at this point B, if I wanted to find the space under those two curves, then the definite integral would tell me that. And so the indefinite integral spits out a function. The definite integral spits out a value. It tells you a value, so it's going to be a number. Now, the other interesting thing about it is that this number can be positive or negative, or it could even be 0. So say you have this function, and you're wanting to find the indefinite integral from here to here. Well, what's the area under the curve? This one's pretty easy. The area under the curve is like that. What's the area under the curve on either side of it? Well, this one on the left, I'm pointing to it like you know what I'm talking about. This one on the left, that one, like we couldn't shade under it, right? Because that would be like, it would go on forever if it was under it. So really it has to be shaded here in between the curve and the x-axis. And same here. This has to be shaded in between the curve and the x-axis. But actually, you know what? I'm going to shade those a different color because what you notice is those are below the x-axis. And so those are actually negative values. I know it's weird to think of an area as being negative, but it can. It can have a negative value if you think about, you know, the market. Maybe we're talking about a stock market or something, and the x-axis is 0. It can go, you know, bank accounts, all of those things. They can go negative, then they go positive, and then they go negative again. And so you can think about how much did it accumulate from here to here, right? So it was negative, negative, negative. All of this accumulated up. Then this positive accumulated, and then this negative. And so you would add all 3 of these together, and you'd end up with whatever. This one looks like it's maybe more negative than positive. So in this case, the integral really could be a negative number. And that's like the accumulation under the curve. So that's basically the idea behind definite integrals. And so let's look at how they're different than a definite integral. So you see the definite integral is written there in purple, and the indefinite integral is next to it. So what do you notice that's different? I mean, really, the only thing that's different is this a and this b, right? And as you probably can guess, this a is the lower bound of our area that we want, and the b is the upper bound. So really, that's it. that tells you what part of the integral you're actually evaluating. And again, you're going to be spitting out a number. It's going to be a number. It's not going to be like a function. So the cool thing about it, because it's a number, it's just like derivatives where we're finding a value at a point, that we can actually do this on a calculator. So go ahead and get your calculators out. And that's the first way we're going to show you is on a calculator. And then we're going to see how to do it the other way. So let's go ahead and get this up. Okay, and I apologize for the low tech way of doing this. I have videoed this more than I'd like to say tonight. This is probably like the 5th video. And because, yeah, all of the different tech ways I was trying to do it just didn't work. So we're just going low tech. It's going to be a little shaky. We're going to do our best. Okay, so here we go. The first function that it asks us to find the integral of, and there's 2 different ways to find the integral. So we're going to start with the Calc menu, but the first one it asks us to find the integral of is x cubed minus 6x. And so we go ahead and put it into y equals and we graph it. There's our graph. And to find the integral, we do second calc. And you come down to number 7, you see there's a little integral sign in front of it. Push enter and it asks you for the lower limit. So in this case, the lower limit is -3. So remember to use the negative sign and not the subtraction sign. And then it asks for the upper limit, which is 1. And I push enter. And look at that. Isn't that cool? So it shades in the curve. And you see some of it's below the x-axis and some of it's above. And in this case, our actual integral is 4. Our final integral is 4. So that's the value of those underneath the curve. Now, the next one asks us to calculate with different bounds. So our upper limit and lower limit are going to change. So we're going to go back to the integral. It's going to ask for our lower limit. We're going to say negative square root of 6. And our upper limit is the square root of 6. And look at that. It shaded the rest of it in. And it turns out the integral there is 0. So it has exactly the same amount below the x-axis as there is above the x-axis. And then there's the other one we want to look at is the absolute value of the same function. So remember the absolute value is in our math menu. So we go to math, go over to number, push absolute value, and we do x cubed minus 6x. Oops, but do you see I forgot to do, when I did the x cubed, sometimes you have to push arrow over, otherwise it stays up in the exponent. We don't want that. So we're going to graph that. Remember, all the absolute value does is it takes all of our y values and it makes them positive because that's what absolute value does. We're going to go to second calc and we're going to find the integral, and our lower limit is -5 and our upper limit is 5. So it's going to go ahead and shade it in. Look at that. Isn't that cool? It's like the Batman symbol. We should do like a contest where you guys make different cool pictures on your calculator. So there's our integral. And if I get really close, you can see that the integral actually is equal to 198.50115. So that is the calc menu. It basically just uses the graph to calculate the integral. Now, the interesting thing is there's actually another way to do integrals on our calculator, and it's actually more precise. So we're going to use that to find the integral of this one. Now, I would suggest you keep it here in y equals, because then you can use it. You don't have to retype it. But we're going to quit. We're going to go back to our main menu. We're going to push math. You're going to go down to fint. fnint. It's number 9. You push enter. Now, some of you are going to have this. And others of you, if you have a slightly older operating system, it's just going to look like this, fnint, and then parentheses. So if you have fnint in parentheses, this is what I want you to do. You type in the function, the variable, the lower limit, and the upper limit. Okay, I'll do that again. The function, the variable, the lower limit, and the upper limit. In this case, you typed in the function as a whole. In this case, you use the vars menu to get the function. But either way, function, variable, lower limit, upper limit. Okay, because it's really not like intuitive. It doesn't tell you like the other ones. But if you have the newer operating system like this one, it just shows you, and all you have to do is put those in. So we put the lower bound in, and we put the upper bound in, and then we put the function in. So you could type in absolute value here, or I like to use the vars menu because I already have it in there. So I go to over y vars and function, and I pick function number 1. Oops. And then it asks d, that's our differential. So what are we integrating with respect to? With respect to x. And I push enter. And you see it's thinking. It's thinking. It's working very hard. 198.500034. So that, and see, that's actually a slightly more precise value for the integral. So this is your value. So this is the way that we're going to do it from now on. We're going to use the math menu. It's a little bit more precise, but just know that that graph menu is available, and it's really cool too because you can see it. So I actually quite like that it does that. So I hope that helps, and there's actually 3 more videos on this stuff. I hope that they're not too long, but there's just a lot to learn. It should be easy, I hope, and we'll see.